Hi everybody. So in today's lecture, I'd like to talk to you about iterative predictions of motion for a varying net force. And of course, this goes along with some material from Chapter 2 of Matter and Interactions 3rd edition by Chabay and Sherwood. So first of all, I'm going to review a couple of things that were covered in other lectures. So if some of this doesn't sound very familiar, please do see those other lectures or reference Chapter 2 of Chabay and Sherwood's Matter and Interactions. Okay? So we're going to review how to write the spring force as a three-dimensional vector. So to do that, Matter and Interactions defines the vector L. The vector L points from where the spring is attached to the location of the attached mass. So shown here in this cartoon from Matter and Interactions, that points from the point where the spring is attached here at this wooden board all the way down to the mass at the end of that spring. So that's the vector L. Now we use the term L naught or L sub 0 for the length of the spring when it's relaxed. Okay, so that's the unstretched or compressed length of the spring. We define the stretch of the spring S as the magnitude of the vector L minus L naught. Okay, so S would be the displacement of the vector from equilibrium. If we do all that, then we can write Hooke's law as the force from the spring is equal to minus KSL hat, where, remember, K is our spring constant or spring stiffness, units newtons per meter, times the stretch of the spring S, and then pointing in the direction of the vector L hat. Remember that this doesn't have any issues with units. Lots of times students think that L hat also has units of meters, but it doesn't. Remember that unit vectors are dimensionless vectors and only indicate a direction. Okay? Also remember that when you model simple harmonic motion, that you get a sinusoidal function out. So this is not considering any damping or driving forces. We'll cover that information later. So for now, it's an undamped, not driven spring. Okay? So if that's the case, then in one dimension, you have simple harmonic motion position with respect to time of a times cosine omega t plus phi. A here is the max displacement from equilibrium, right? So that's the amplitude of the motion. Omega is the angular frequency, and phi is the phase constant, which is basically just how offset the sinusoidal curve is from t is equal to 0. When did you start your clock, right? Omega, remember, is the square root of k over m, where k is your spring constant and m is your mass. It's an angular frequency, so its units are radians per second. Okay? Your angular frequency is related to your regular frequency by 2 pi f. Remember that the regular frequency is the number of oscillations per second. And then the frequency, of course, is 1 divided by the period. So that means that omega is equal to 2 pi f is equal to 2 pi over t, where t, capital T, is the period. The period of the motion, remember, is the time that it takes for the oscillation to complete one cycle. Okay, now we're going to introduce some new commands in this video. So there's some functions that are available for working with vectors. Specifically, it makes it easier to take the magnitude of the vector. Remember that theoretically what you do to take the magnitude of the vector is you do the square root of the sum of the squares of the vector components. But as that's kind of time consuming to type in, VPython has very cleverly created a really quick command to take that magnitude for you. And so if you have a vector A, you can take the magnitude of that vector using the word mag of A. Okay? Now this is of course assuming that you have already defined your vector A previously in your code and that you've defined it as a vector. So if you start getting error messages from your code, that might be why. Check and make sure that you defined it as a vector to begin with. Okay? So mag of A, that finds the magnitude of the vector. Now you can also find a unit vector in a really short piece of code. Remember that to find a unit vector theoretically, what you do is you take your vector and then divide it by the magnitude of that vector, okay? But there's two ways that you can do this in just a few characters, and that's norm of A, that gives you a unit vector in the direction of the vector, or hat of A, so you can pick your favorite. I like hat because it's easy for me to remember. Remember that the hat convention is because usually the way that we write a unit vector is to put that little caret symbol over the top, which is usually, when we say it out loud, called hat, like L hat, right? So there's two ways to find unit vectors. So I'm going to use mag of A and hat A in the code that I'm going to show you in a minute, where I model a mass on a spring. Okay, now we're going to use an example using the iterative technique. We covered the iterative technique for modeling of motion with a constant force in a previous lecture. And what we're going to do in this lecture is very similar, of course, except for the fact that the spring force isn't constant. It changes. So remember that the iterative technique says the following things. First of all, you calculate your net force vector acting on the system. Then you use that net force to update your momentum using the momentum update equation. The momentum update equation is that your new momentum, or final momentum, is equal to your old momentum, or your initial momentum, plus your force that you just calculated times delta t. Okay? So that's your momentum update equation. After you update your momentum, you're then going to update your position using the position update equation. Remember that the position update equation is your new position, or R final here, is equal to your old position, which is R initial, plus your average velocity during that time step times the time interval delta t. Okay? So remember that you calculate your average velocity by taking your new momentum P final here and dividing it by your mass. So that's also a step that needs to be done within your code. Okay? All right. So the only difference that we have here from the constant force that we covered previously to the variable force, which we're covering in this lecture, is if you have a constant force, say, for example, gravity, right, on planet Earth, like in projectile motion, you could actually calculate your force outside the loop and it doesn't change, and that's it, okay? But in this case, your calculation of your net force needs to be included within the loop, okay? And you need to update that each time you go through, right? It has to, calculation of the net force must be included within the loop if your force varies with time. So that's the main difference between what we did in a previous lecture and this one now. The example that I'm going to work is from problem 43, chapter 2 in matter and interactions. So I'm going to even go a little beyond what they asked for in this question. This question was originally designed to make you manually do the calculation with a very large time step. I'm going to take a much smaller time step and model the motion from time t is equal to 0 on, okay? But other than that, I'm going to reference this example. So let's read it together. A block is attached to the top of a vertical spring standing on a table. The spring stiffness is 55 newtons per meter, the spring's relaxed length is 23 centimeters, and the mass of the block is 350 grams. The block is oscillating up and down as the spring stretches and compresses. At a particular time, you observe that the velocity of the block is 0.08770 meters per second, so I just gave the components x, y, and z there, okay? And the position of the block is 0.07980 meters relative to an origin at the base of the spring. Using a time step of 0.1 seconds, determine the position of the block 0.2 seconds later. Okay? So what I'm going to do is set my initial conditions at t is equal to 0, matching the velocity and the position of the block as given in the problem. But then I'm going to take a much smaller time step and just let the clock run and model the motion as a whole, and then graph that motion. So that's what I'm going to do with this code. Okay? So let me show you my code. I'm showing it here on the PowerPoint because the text is a little larger when I do it this way. But then I'm going to go ahead and run the code in Glowscript for you. But this is just a copy and paste job. Okay? So let's discuss this code line by line so that we all understand what's going on here. Okay? Of course, the first call is always the same for the VPython programs if you want to visually model the motion. And that's from Visual Import Star, and it calls the whole visual library. But I also want to make sure that I can make a graph of the motion. Okay, so I want to make a graph, not just show the block bobbing up and down, but also graph it. And to do that, I've got from visual.graph import star, and that calls the graphing package. I'm going to have a smaller time step than is suggested in the problem. Okay, I chose 0.02 seconds. okay, for my time step. I initialize my clock at t is equal to 0. I'm going to start my clock at 0. Okay, now, first of all, I'm going to define my variable for the momentum based upon the initial conditions as laid out in the problem. So, P block, which stands for momentum of my block, is going to be the mass of the block times the velocity, okay? And this is going to be the value at t is equal to 0 for the velocity so that I can effectively model the motion. So that's going to be, the mass is 0.35 kilograms, okay? So I switch to SI units, times a vector, which is going to be my velocity. And that's 0.0877 and 0 as described in the problem. Okay, so this is going to be a plus y initial velocity for my problem. Next, I want to simulate the motion. I'm going to draw a block, okay? Now, I'm not going to draw a spring. I could do that. I could put that in. But right now, I'm just going to have a block oscillating in empty space. And that'll kind of minimize the confusion of this code, I think, because we're just showing one little thing we're focusing in. So I've got a block, which is a box, okay? I've defined the position of my box here, and that is according to the initial conditions laid out in the problem. And so the block's position is indicated here by pos equals vector 0.07980, okay? Now, I want my box not to be too big for the problem. If my box is huge, then the oscillation might not even show up. So I called my size vector here 0.1, 0.1, and 0.1. And, you know, if you guess wrong when you do this kind of thing, it's easy to go back and change and fix that. And I made a green because I like green. And lots of times I turn make trail on. But for this case, since the thing is just going to be bobbing back and forth, the trail isn't going to be very helpful. So I just turned make trail off, make trail equals false. Okay, now, in this problem, there's actually two forces acting on the block. And that's because the block is attached to a vertical spring. So I have the spring force, okay, but I also have gravity. Since gravity is a constant force, I can have the calculation for that outside of my loop, okay? Now, if this is confusing to you, of course you can put it within the loop and have it calculated each time, and that's up to you. But since it is constant, I just had the calculation outside of my loop, okay? So gravity is, of course, mg, and that's going to be the mass of the block, which is 0.35 kilograms, times the acceleration due to gravity, which is going to be shown here, 0 minus 9.80, and it is a vector, of course, and minus sign for gravity going down, okay? All right, now, remember that our equation for the force for a spring in 3D was F is equal to minus K S L hat. So that means that I have to define my L vector, okay? Well, what I've got here is basically motion in just y, one dimension, but I do have sort of an assumed thing here that I'm going to put the attachment point for my spring at the origin, okay? And then that would mean that the L vector just points from the origin to the block's position at any given time. So I've defined that here, initializing that value as L is equal to block.pos. But bear in mind that it would be L is equal to block.pos minus the attachment point. But since the attachment point is 0 for this problem, I didn't include it, okay? Okay, so hopefully that's clear. Now I need to find L hat because it's minus KSL hat. No problem. I'm going to initialize that variable by saying that L hat is equal to hat of L. Okay, so there it is. Okay. Now, yes, if you're a VPython expert, there are other ways to do this, but I'm showing this one. Okay. Now, L naught is the equilibrium length of my spring, which was specified in the problem to be 23 centimeters. So L naught, which is a scalar, is 0.23 per 0.23 meters. S is the extension of my spring, which would be the magnitude of my vector L. Wherever the block is at that time, I take the magnitude of that vector to figure out how far it is from the origin, and then subtract off L naught, okay? So mag L minus L naught, that's the extension of my spring. I'm also going to define my spring constant here, and it's 55 newtons per meter, okay? So I've done that here. So here's my definition of my variables and my front matter of the code. Remember that your front matter of your code should include calls to any packages that you've got, right? Like these graph packages. I should initialize my clock, initialize all my variables, and define all my variables before I get into my loop. Okay? Now, another thing that I need to do, since I'm going to be plotting the motion in a graph and not just visualizing it, is I need to name my graph. Okay, so I've decided to plot the y position of the block versus time in my graph. So not very originally, I'm calling my variable for the graph y block. Okay, and this is how you code a graph in VPython. It's using the term g-curve, and then you tell it what color you want your graph. And so I've got color is equal to color.green to match the color of my block. Okay, so that's what I'm doing there. All right. Now, this is all my front matter, and now I'm going to get into my iterative technique where I update everything as I go along. So to do that, I need a loop, and I ran my time out to 3 seconds for the loop. Remember that if, of course, you're running your time and it's not the right time, you need to extend it or shorten it. It's easy to do that in editing your code. So I just said while t is less than 3 seconds. Okay. I defined a rate of 10 so that we could watch the block bob back and forth and, you know, not have it look like it's jerking all over the place. So I defined my rate of 10. That means it's going to run the loop 10 times per second. And now, remember, the first step in this iterative technique is to find my forces. Okay? So the force of the spring is minus k times s times L hat. That was our equation that we had for 3D modeling. So minus k times s times L hat. Remember that I initialized those things, so when I first go in to the loop, it'll see the initial values that I defined above. Okay, next, what I need to do is use my momentum update equation, which is P final is equal to P initial plus F net times delta t. So here, I've got my P block. Remember, my initial values of P block are defined here in the front matter. So P block is equal to the old value of P block plus my force, my net force times delta t. Now my net force will be the sum of gravity and my spring force, because both of those are acting on my block. My gravitational force will not change, so I put it outside my loop, but my spring force will, and the calculation of that is included in the loop. So F gravity plus F spring times delta t. Okay, so that's my momentum update equation. The next step is my position update equation. So that one was, you know, R final is equal to R initial plus V average times delta t. Okay? So what I've got here is block.pause is equal to block.pause plus P block times delta t over 0.35. Remember, the way they calculate V average is to take your momentum and divide it by your mass. Okay? Okay, so I've got P block divided by 0.35 kilograms times delta t. So that's my momentum update equation. Okay, now that I've updated my momentum, what I'm going to do is say then that L, my new value of L, is equal to block.pause, because I can't leave it, see. L was initialized here, but if I update my L vector, if my L vector changes, I need to update that within my loop, so that when I go back through the loop again, that I've got the right values for S and L hat. So to do that, I need to update my value for L. So L is block.pause, right, with an understood minus 0 for the origin, right? I update my value of L hat. I update my value of S, okay? And now I'm ready to go back through the loop again, okay, when I need to. Then I increase my time step. T is now equal to T plus delta T. And then at the very last thing I do, I plot that data point so that it's visualized on the graph, in addition to showing the mass moving up and down. So y block dot plot is equal to, and then here I add a data point where the I've got the time and the y position of the block. Okay? So that's it. Okay? In doing this, I have completely modeled the motion. So now, let me run my code. Okay. And you can see here, move this out of the way, you can see here that my block is moving up and down. Now it looks a little silly because it's moving up and down an empty space with no spring attached to it. But modeling that would add an extra line to the code and create a little bit more confusion. I wanted to avoid that, okay? So here's my block bobbing up and down in free space, and then here's my plot of my motion for my graph, okay? So there you go. That's how to do a model with a changing force, and how to do all that in VPython. Oops, wrong thing. Okay, so the punchline here. In Chapter 2, matter and interactions doesn't really go too much into the theory of springs, right? They just kind of define Hooke's law and let it go. And they define Hooke's law so that you can use that force in your iterative technique, right? You can code it in. Now, the theory of the question is a little harder than some theory that we've covered in class previously. In other words, in this problem, there's gravity and the spring force. And we didn't cover that theory. We will later, but we haven't covered that theory yet. But the thing is, you don't need that theory to model it, do you? You just need to know how to calculate the force at each time step, and you know how to do that. So you can sometimes use the power of this tool to model things. As long as you know what the force equations are, you can model it even if you can't figure out the analytical solution. That makes it very powerful. Now, of course, these are most useful if you understand both, and then you get a deeper understanding of things. I'm not downplaying analytical solutions at all. I want you to know how to do both. But this will give you an intuitive understanding of what's going on with these springs, and I think that's really important. So we coded it no problem, just applying Hooke's law, and I think that's awesome. Okay, well, that's what I wanted to get at in this lecture. I hope you enjoyed that and understood it. Let me know if you have any questions, and as always, I'll see you in class.